atoms and things of carbon. So if you remember, carbon has 3 p orbitals and 1 s orbital, right? And to make bonds, we have to hybridize those, right? And the most common one is our sp3, right? So that sp3 gives us our base shape, right? So we have our orbitals like this, and I'm excluding the anti-bonding orbitals, right? To get this, if we put in our anti-bonding orbitals, right, we have these little anti-bonding lobes going back, right? And that actually is for the SN2, right? That's what it's actually reacting with, is those anti-bonding orbitals. So a little bit of that. So let me draw a couple of structures. Give me the hybridization of the marked arrow atoms. So let's take a little time. Give me the hybridization of those atoms that are marked. Okay, let's take a look. Again, hopefully this is going to be pretty quick. Okay, one of the things to remember on here, and again, I'm drawing the form that you're most familiar with now, but one of the things you want to do is draw all of your, lone pairs and your hydrogens of it's not of all of it, but the hydrogens at least of the atoms that I'm pointing to, right? So if we're looking here, we've got three atoms attached. If we have 3 atoms attached, right, how many sorry, this one, if we're looking here, right, 3 atoms attached to that carbon, that means we're going to need hybridized orbitals for 3. So therefore, we're going to need sp2. Right? If we look at this carbon, how many atoms do we have of that carbon? Well, I have 4 carbons added. So therefore, I'm going to need S. And then how many P's to come up with 4? Well, I'm going to need 3, so sp3. Over here, again, we look at how many atoms. So I have a carbon, carbon, and a hydrogen, right? So we're looking at how many bonds do I need to make, hybridized bonds do I need to make the atoms, and that gives us, sp2. All right, on the other one, now I've thrown in a couple of other atoms, but the thing to remember with nitrogen and the oxygen is they're in the same row as our carbon. So therefore we're dealing with S and Ps. And so again, draw in, the lone pairs. Okay, and if we look here, right, a lone pair needs a hybridized orbital. So in our straightforward thinking, right, of how many atoms are attached to, now we have lone pairs, so we need to have a lone pair. So we have atoms and lone pairs. So for the nitrogen, right, I've got a lone pair, that's going to need a hybridized orbital, and the bond to carbon, don't count all the bonds, just call the atoms and the lone pairs, that's 2. So therefore, this is just going to need an S and a P. So this nitrogen is just sp. If we look at the oxygen, 2 lone pairs, right, and 2 atoms, that's 4, so we need 4 hybridized orbitals. And so therefore this is going to be sp3, and then down here again, sp3, we've got 4 atoms. Okay, questions about hybridization and determining hybridizations? Okay. Should be pretty straightforward, but again, it's been a while to do these. Okay, the next one that was important in that area, right, was dipole moments. Okay, so we'll draw a few atoms here and put in the dipole moments. Okay, let's take a little time, put in the dipole moments for these 5. Okay, so if we look at the first one, bond dipoles, the chlorine is going to be more electronegative, right, than the carbon. So we're looking at electronegativity here. That's going to give us a partial negative, partial positive. If we look at the magnesium is less electronegative. So here we have the dipole going the other way, making the carbon partially negative, and of course the magnesium is partially positive. In the next one, we have the oxygen is more electronegative, so therefore we get a partial negative and a partial positive. In this one, the chlorine is more electronegative. All right, so we have dipole moments going in all 4 directions. Here we have dipole moments between the carbon and the oxygen. So if we look at these, right, we've got all those dipole moments. Now let's come back and put in molecular dipoles. All right, so for molecular dipoles, what we're looking at here is really a vector addition of the bond dipoles. So if we look in the first one, really the molecular dipole is going to be going in the direction of the chlorine, right? Here, it's going to be going in the direction of the carbon, and then here it's going to be going in the direction of the oxygen. But when we get down to the tetrachloride over here, now they're all going in 4 directions that are symmetric, and we have the same atom on each one of those, so that's symmetric. So here we use nu equals 0 because our molecular dipole will be 0. In the next one, we have dipoles going towards the oxygen, right? So therefore our molecular dipole is then going down towards that oxygen, right? But we're equaling out those 2 vectors, then it's just going directly down. Okay. All right, questions about dipoles? Let's look at intermolecular forces. Give me the intermolecular forces that would be the main contributor for these three. All right, the first one, and I'll give you more time whenever the problems get a little bit more complicated. The first one, this one's going to be hydrogen bonding. B, D. Okay. Here we have the dipole going this way, so it's going to be dipole, dipole. Right here we have no dipole moments, so this is just going to be van der Waals, or also known as London dispersion. Okay. From intermolecular forces, we can get to boiling points. So rank these compounds for their boiling points. Okay. Rank those, and then also rank and we'll do a couple of series here. So give you a little bit more time on these. And to make it easier, well, all right, let's take a look. So what we're looking for here is a few concepts. One is, what are the intermolecular forces? And then also then what is the potential packing? So the first one here, we've got alcohols on all three of those, which means all three of these are going to be hydrogen bonding. Okay. So since they're all in the same, then where we're going to be looking for is size, right, and structure. Size, the bigger it is, the higher the boiling point is going to be, because it's got more atoms to interact with other molecules of the same thing. The smaller it is, the less atoms or interactions it can have. And then structure. A simple structure is going to be able to pack closer, meaning we're going to get, in this case, better hydrogen bonding, where a complex structure or one with a lot of steric interactions aren't going to be able to pack as close. So therefore, that's going to be a lower. So the closer the molecules can get together in the bulk, the better the hydrogen bonding, the stronger the forces between them. So therefore, the higher the boiling point. So if we take size and structure together, that means that this one is going to be the highest boiling point, right? And then if we look at 2 and 3, well, 3 is really pretty small. That's ethanol. So that's probably going to be the lowest. And then we look at 2 will be in the middle. 2 is less than 1 because it's got this irregular structure that's going to keep it a steric structure, right? That's going to keep it from packing as closely together in a combined unit. Also, it's got a chiral center, and we'll get to that later, right? It's got a chiral center here, which means that you also potentially have R and S in the same solution. And if you have R and S in the same solution, that's also going to keep it from packing. So size, 3 is the lowest, and then structure, 1, it packs better than 2, so therefore it's a higher boiling point. On the next one, we're looking at very similar sizes right across the board. But if we look at the type of interactions we have, we've got ionic, right? Because that's going to be negative and that's going to be positive. We've got hydrogen bonding. We've got dipole. And we have van der Waals or London dispersion forces created by instantaneous dipoles. Right, so this one's pretty straightforward. The ionic is going to be much stronger than the hydrogen bonding, which is going to be stronger than the dipole, which is going to be stronger than the van der Waals, London dispersion or van der Waals. Okay. Okay, let's try one more of these. Well, I think we can move on. Any questions about boiling points? Okay, let's figure out the formal charges for the atoms indicated. Okay, let's take a look. So for member formal charges, what we need to know is how many electrons we have around it. So when it's a bonding pair, we're going to say that it has 2 less, right? So we'll start with our 4 because carbon has 4 electrons. Then if we look at the bonded pair, right, we're going to take half of those. So that's going to be half of the bonded pair. So that's 6 divided by 2. So that's going to be 3. So we'll subtract 3. And then our lone pair, which here we have to use both of those, right? So our lone pair gives us -2. and then do the math on this one, and this one should be a -1, right? So here we have a -1 formal charge. By this point, you probably have this down and can just look at it and know, but this is the process. Here again, if we look at our carbon, we have 4, we got 3 bonded pairs, right? So take half of that. So the 3 comes from 6 divided by 2, right? Because we're going to split those in half. We subtract because it's electrons, right? And then so if we do that, this gives us a +1, and we can see that looks like a carbocation. For the nitrogen, now we start with 5, right? We look at our bonded pairs. So we have 8 electrons in there divided by 2, so that gives us 4. So we subtract 4, and that gives us a +1. Okay. So we get +1 there, and so we can see that that's nitrogen is +1. So formal charges, something you probably haven't done in a long time. Probably assume I draw them very quickly when we're doing structures, but do expect something along the line. Some of these simple things can throw you off. You don't at least review it real quick. Okay. Resonance structures. Probably something that kind of caused you problems in exam 1, but hopefully by now we've worked through a lot of those. So let's try a few. Draw me all of the major resonance structures for these two, and then we'll do some more in a second. Okay. All right, let's take a look. When I'm doing resonance structures, I always like to look at what's going on. So we always go from high electron density to low electron density. So that can be a negative charge, right? Or that could be it's also a good idea to go ahead and show your electrons, right? So we already had 2 electrons there. So our first structure is going to be this one where we've created that double bond, right? We have a negative charge now up here. I don't know why I put it in blue. But we have a negative charge here. Now, if we think about it, is there anything else we can do? Well, this over here, right, is an sp3, is an sp3 carbon, right? And so I can't break a bond for a resonance structure. I can move electrons, but I can't break connectivity. So carbon-carbon, we can't break atom-to-atom connectivity. So we're really dealing with lone pairs and pi bonds, right? If we start to move sigma bonds, are single bonded, that's a hybridized orbital, then we're going to be breaking bonds and changing the structures. So this is the only resonance structure for this one. If we look at our next one, put in our lone pairs and our oxygen. Okay, we'll move from pi bond to positive, so from high to low. The result of that will be this one. Okay. And then can we do anything else here? Not without breaking our pi bonds, right? So at this point, that's all we got. So we just got 2 resonance structures. Okay, questions about either of these? Right. Let's try one, a couple with a little bit more. I don't like that example. Okay, let's try these 2. Okay, in the first one, we got positive here. We're going to be moving the electrons. So first we move them here, which gives us this structure. The positive there. And then we can move those again. Positive there. Okay. And of course, this is sp3 here. So we don't go through that one for our resonance. Here we've got the nitrogen, the lone pair. This pi bond can go up here, moving the electrons there. Giving us the carbocation there. And then we can move these electrons towards that carbocation to give us carbocation there. Okay. Questions about resonance? Okay. All right. Next, let's look at acids. So we're moving into the acid chapter. So let's do some conjugate acids and bases, right? And what we'll focus on is, I'll put it out here. So let's start with some conjugate bases. Okay, so let's draw the conjugate base for these four. Let me give you a couple more. Let's try these 5. The last one I erased it. It turned out it wasn't going to be good. What was the question about the ketone one? What was the resonance structure? This is the resonance structure for the ketone one. We just move the electrons up to the oxygen. Right. So if we look at the conjugate bases here, okay, we're going to be extracting the most acidic acid proton. So in most cases, we want to find the most electronegative atom, right? We can also think about arrow, right? So that's atom, resonance, inductive, and orbital. Right. So here we look at it, the hydrogen on the oxygen is going to be the most acidic, so the conjugate base is going to be that. Here we look at it, this is sp, right? That's sp3. So we get all the way to the orbital. So therefore the conjugate base here is going to be this one. Here we've got the hydrogen here, right? Attached to a more electronegative atom. That's my conjugate base. Here it's thrown off a little bit because it's got a positive on it. But if we lose the proton on there, we just end up with this species, right? The nitrogen. Here we have 2, and this is something to watch for. You'll see multiple potentially acidic. I mean, all of these kind of had the sp3 carbon, but here we have 2 different ones. We have 2 different electronegative atoms. And on this one, right, the oxygen on the acid is going to be the most acidic because it'll give me the resonance structure, right? So let's look at acids. So conjugate acids. Okay. Okay, let's do the conjugate acids, and I'll leave it on conjugate bases for a while. Okay, I'll leave it on basis so y'all can pick those up. So our conjugate acids, we're going to look at the place that we could protonate to give us the most stable groups. So I'm going to put my lone pairs in. So we want to look at those. So for the ketone, protonating the alcohol, right, gives us the most stable positive. In the pyridine, we're going to protonate the nitrogen. Here we have two different oxygens. So in this one, we have this oxygen here and this oxygen here. If we look at this oxygen, if I protonated this oxygen, I could actually potentially stabilize that oxygen with the sp2 carbons. Here, if we look at this, because that's more electronegative than the sp3 carbon. So therefore, this one is a very slight difference, not a huge difference, but a slight difference. And we see this as our preferred because of the hybridization of the carbon it's attached to. And then this one, it's a little different. You wouldn't have seen this in that chapter, but this is the way you would protonate that. The alkene gets protonated here. Okay, so that's conjugate, right? Simple question we'll get in these. Now let's look at ranking. So let's rank some acids. I won't expect you to know any pKa values directly except for water, right? 15.7. But I would expect you to understand pKa values. So if I gave you a set of molecules and their pKa values, I would hope you would know that a low pKa value is more acidic than a high pKa value. But I would give you the molecule and the pKa value. But 15.7, it's always good to know where your set is in any scale, right? And so water is a good set for pKa values, so you know where you are. So let's look at ranked acids more based on the qualitative, that ARIO concept. So I'll give you 4 acids and you rank these acids. Okay, let's take a look. Okay, one of the things to think about when you're doing this is that it's hard, visually, it's hard to look at these molecules that you know are stable and think about their acid strength. So one thing to do on these is to go ahead and show the anion, right? So we're looking for the most stable anion. The conjugate base of these is going to be the one that's going to be most acidic, and the least stable, right, is going to be the least acidic, right? So the equilibrium would be shot the other way. So if we look at these, we have two with resonance, right? And resonance, all the atoms are the same. So we have oxygen, 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 oxygen. Resonance, right? We have resonance here and resonance here. No resonance in these two. We have inductive here. Right, so we have inductive here, here. And if we look at our orbitals, right, all of our orbitals of our oxygens are the same. So all of these are going to be sp3 hybridized orbitals. So therefore, if we look at atoms, they're all the same, and resonance. So we're really looking at resonance and then inductive. So this one has resonance and inductive, meaning that's going to be the most stable, which means that's the most acidic, right? So it would be the one that could go. Then we have resonance at this position, right? So that means we have one here. Okay, and then we have inductive at this one, so that makes that third. And then our last one is the one that's just the OH, okay? On this one, if we look at it, we need to show our conjugate base. Now, by showing our conjugate base, we're actually kind of giving away a few things, like I'm taking the conjugate base off of the sp3s, not off of the sp and the sp2, not the sp3s. This one, I have no choice, right? I have to take that proton, giving me negative here, and then this one, I take it off the nitrogen. Right. So if we look at atom, it would seem like our nitrogen is going to be the most important, but we have to also remember that this is an sp3, where this is an sp. And in most cases, you're going to be dealing with the same orbital range, right? This is the reason I put this one in here, is this is one that's going to be, you need to remember this. One of the things to remember, now that you've already gone through the later chapters, is that I can take this compound with this compound, and quantitatively, right, I can end up with this. Okay, and this goes forward, which means that this, right, and that means that this compound is more acidic than this one, right? Because the reaction goes forward, and we know that the pKa difference here, right, is about 35 and about 25. Right, so we have that difference, right? So this is going to go down. So therefore, if we're looking at this, it's pretty straightforward to think about the fact that, you know, if we're looking at these, that the sp3 is going to be the lowest, and then we have the sp2, right? But then the problem becomes that it's actually the sp carbon hydrogen that's more acidic than the nitrogen. Okay. And of course, now we have this reaction. Okay, so this is one of those, this is about the only one that is out of that order, right? Usually our atom is the most important, but in this case, the atom, the nitrogen to the oxygen, wouldn't be the case for oxygen, right? But for the nitrogen to carbon is different. Okay, questions about acid? Oh yeah, the first one is 2. Yeah, thanks. Okay. Yeah. All right.